this video, we'll talk about linear PDE types. Okay, there are three major types: elliptic, parabolic, and hyperbolic. Okay, and elliptic PDE is defined as such, where you have second derivatives in terms of the spatial coordinates x and y summed together, and you can assume that they have a coefficients in front of them, but they're always positive, and hence it's a type of an elliptic PDE. A parabolic PDE has the form of this type, where you have second derivatives of the spatial coordinates that equals to the first derivative with respect to time. Such problems are commonly found in heat transfer, as we have seen in our introduction lecture, and commonly solved with a finite difference method numerically. The third type is a hyperbolic PDE, and this is a special class of problem where you will have a differentiation with respect to the spatial coordinate equal to the differentiation with respect to the temporal coordinate. And similarly, you can define hyperbolic PDE for second order differential equation, which is simply the second order differential with respect to a spatial coordinate, and that equals to the second order differentiation with respect to the time. And this can be also written in a two-dimensional format as well. Example of such a hyperbolic partial differential equation is a wave equation. Hyperbolic equations are notoriously difficult to solve. Solve numerically. And even though you have recognized this PDE as the one we have derived in the previous lecture, finite element analysis is actually not suitable to solve this type of PDE, hyperbolic PDE, numerically. So what we do is we assume a steady state condition. Okay, so we convert that into an elliptic PDE by assuming a steady state condition. Okay, and this is a valid assumption because in most of the statics or mechanics problem, we can assume that the variation of conditions with respect to time is very slow. Hence, the double time derivative of a variable u, or displacement, can be ignored and can be assumed to be a steady state instead. And that makes it much more easier to implement into a finite element framework and have a possible numerical solution. Okay, so as you have guessed by now, in this class we'll only focus on elliptic PDEs that represent the steady state